On behalf of the Princeton University Mathematics Department, I'd like to welcome you to the first lecture of our second Minerva Lecture series. They'll be given by Professor Ian Agol of University of California, Berkeley. So the Minerva Lectures are generously funded by the Fernholz Foundation. And the Fernholz Foundation was created by Louisa and Bob Fernholz and is directed by Louisa Fernholz. So now I'll give an introduction to Professor Agol. So Ian Agol received his PhD from UC San Diego, working with Mike Friedman as his thesis advisor. And in the last 10 years, he has made many fundamental contributions to the theory of hyperbolic geometry, three-manifold topology, and geometric group theory. So I'd like to mention some of these really great contributions. Well, to start with, he proved the Marden tameness theorem, which has many applications in hyperbolic geometry and three-manifold topology. In particular, in the 1970s, Thurston more or less reduced the Alford measure conjecture to the Marden tameness conjecture. So therefore, this proves the Alford's measure conjecture. And for this, he shared the 2009 Clay Research Award. And second thing is, suppose you have a closed hyperbolic three-manifold, and you have say a simple geodesic, and you take this manifold and drill out a tube about this geodesic. Then he found sort of an interesting relation, a way to compute the lower bound of the volume of this closed manifold in terms of the volume of the cusp manifold, the drilled out manifold, and the radius of this tube. And I mean, this is very interesting for a number of reasons. To start with, this was done, well, with joint work with him and Nathan Dunfield. And this gave, so the first, as far as I know, the first application of Perlman's work on Ricci flow to a problem outside of geometrization. And second, it played sort of a crucial role in sort of the ultimate proof that found sort of the lowest volume closed orientable hyperbolic three-manifold. And sort of another big contribution was that he found sort of a relatively simple algebraic condition on, say, a closed hyperbolic three-manifold for that manifold to have a finite sheeted cover that fibers over the circle. And for this paper, he very recently won the 2012 Senior Berwick Prize of the London Math Society. And very recently, Professor Agol solved a conjecture of Danny Weiss. And this conjecture implies, well, a consequence of this is sort of many things, and we'll be hearing about them in this lecture series. In particular, it gives sort of a positive solution to Waldhausen's virtual Haken conjecture. And this conjecture has been sort of a focus of just tremendous interest and effort in the last 40 years. And other applications, it shows that the fundamental groups of hyperbolic three-manifolds have just some amazing properties that are beyond sort of other amazing properties that come from knowing that these are sort of discrete subgroups of SL2C. And finally, another consequence is that these groups satisfy the necessary condition that Ian showed implies sort of virtual fibering. So consequently, he proves the virtual fibering conjecture of Bill Thurston. So So now please welcome our speaker, Professor Ian Agol.
All right, thanks, Dave, for that introduction. He neglected to mention that he also solved the Themis conjecture with Danny Caligari and shared the Clay Prize with me. So that'll actually come up in the lecture a little bit today. So yeah, I want to thank Dave and Manjul for their hospitality and the invitation to come speak here. It's a privilege to be here. And so I'm going to give a few lectures on centered around my recent work that Dave just mentioned, but hopefully I'll be able to set it in we'll give some background and set it in some historical context. Okay, so the motivating, starting point for, I think, a lot of the work that's been done in three-manifold topology in the last 30 years or so, and in Kleinian groups, is a paper of Thurston, a survey paper in the Bulletin and AMS in 1982 called Three-Dimensional Manifolds, Kleinian Groups, and Hyperbolic Geometry. And it sort of laid out Thurston's viewpoint on three-dimensional manifolds and their relation with Kleinian groups. And at the end of the paper, and I still recommend it as a good introduction to the subject if you haven't had a look at it. It's really a nice paper to read. So he asked at the end of the paper 24 questions, which have really guided a lot of research for the past 30 years or so. So the first question is the geometrization conjecture that Dave just mentioned. And there's some other conjectures in Kleinian groups that have been resolved in the past decade or so, the ending elimination conjecture and the Themis conjecture. So there's been a lot of work done on these problems. And I want to focus, these lectures will be focused on 4 of these questions, which have to do with what's been referred to as virtual properties of three manifolds. So I'll explain virtual in just a second. So question 15, paraphrase, is are Kleinian groups Slurf? Question 16 says, does every aspherical three manifold have a finite sheeted cover, which is Haken? And this question, as Dave mentioned, originated with Waldhausen. And question 17, does every aspherical three manifold have a finite sheeted cover with positive first Benny number? And question 18, does every hyperbolic three manifold have a finite sheeted cover which fibers over the circle? And Thurston comments, this dubious sounding question seems to have a definite chance for a positive answer. So clearly he was not conjecturing this problem, but just laying it out as something that I think was a challenge. So the goal of these lectures then will be to explain the meanings of these problems. So I don't expect people to understand all the words in those. So the first lecture today will be going over just trying to explain what these 4 problems are saying. And so there's a lot of background and three manifold topology that goes into this that I'm going to cover in today's lecture. And hopefully I'll place them in a little bit of historical context. I'll explain, hopefully in the third lecture, a little bit about how they follow from this conjecture of Dehn-Wise, again, that Dave mentioned in his introduction, which is really a question in geometric group theory. And so there's, I think, a lot of the interesting aspect of this result is the translation from this topological question. These questions of Thurston's are really topological, or Waldhausen topological, to some questions that are really, the answer is really geometric. So today I'll review some three-manifold theory. The second lecture will be an overview of geometric group theory, or at least the geometric group theory relevant to these questions. And then the third lecture will explain how these fit together. So how Thurston's questions can be reduced to this conjecture of Dehn-Wise, and then I'll discuss some aspects of the proof of Wise's conjecture. So that's the plan for these lectures. Okay, so for this talk, first I'm going to talk about, so I'm not going to give an overview of all three-manifold topology, obviously. That's impossible in a single lecture. So I'm really only going to focus on the aspects of three-manifold topology that are surrounding these 4 questions of Thurston. And And I'll be ignoring all kinds of things, quantum invariance, Floer homology, various contact invariance, all sorts of things. Don't take this as a survey of three-manifold topology in general. So that we'll discuss immersed and embedded essential surfaces in three manifolds, and then I'll talk a little bit about the geometrization theorem, say a few words about that, and then I'll talk about essential surfaces in hyperbolic three manifolds, and then I'll talk about some group theoretic properties of three manifolds, three manifold fundamental groups. So when I say three manifold group, I mean the fundamental group of a three manifold. It's just terminology. And then connections between the group properties and these questions in Thurston's list about virtual properties of three manifolds. Okay, so essential surfaces in three manifolds. So all the surfaces in these lectures will be orientable unless stated otherwise. And, so if I don't say it's not orientable, then it should be orientable. So so what is an essential surface? So a closed essential surface is a map of a surface, a two-dimensional, say, closed surface, into a three manifold, so sigma into M. It's a surface which either, let's say the order characteristic is less than or equal to 0, so it's a torus or a genus 2 surface or whatever. And the map is pi1 injective. And here I'm going to abuse notation. I'm not putting base points, but this notion of injectivity doesn't matter as long as the surface is closed. Sorry, connected, I mean. Or the surface is a sphere, and then essential means that it's homotopically non-trivial map on pi2. Again, there's some base point issue there, but whether it's 0 or not doesn't depend on which base point you choose. So a map of a sphere which is homotopically non-trivial. And if we have an embedded surface, so if sigma injects into M, then, I guess I have a pointer here, let me try this. So if sigma injects into M, is an embedded pi1 injective surface with Euler characteristic less than or equal to 0, then the surface is called incompressible. So this is a classic terminology in three-manifold topology. And the notion incompressible, or the term comes from sort of a geometric picture. So there's a corresponding notion of essential surface in a manifold with boundary, but for avoiding some technical details, I'm not going to say much about that. You can basically just double the manifold along its boundary, and if it's essential, if the double of the surface is essential in the double of the manifold, then it's essential in the relative sense. But I'm not going to get too caught up on that for this talk. And if M is aspherical, so for a three manifold, aspherical means pi2 and pi3 vanish. In general, aspherical means that all the higher homotopy groups vanish, but this suffices in 3 dimensions. So if it's aspherical and it contains an embedded pi1 injective surface, then M is called Haken. So that's the origin of the term of a Haken manifold. So Wolfgang Haken is a three-manifold topologist, and you might have heard of him, Appel and Haken, who solved the four-color problem in the 70s. Is the same Haken. So that's the notion of a Haken manifold. For example, if you have a manifold that's aspherical and it has positive first Bay number, so the first Bay number is the rank of the first homology with rational coefficients, then M is Haken. Or another way of saying this is if there's a surface, again, an orientable surface, and it's an orientable three-manifold, and that surface, when you cut along it, it doesn't separate the manifold, then it has positive first Bay number. You can say this other ways in terms of there's like a harmonic, non-zero harmonic one form, or however you prefer to think about it. And this follows from the loop theorem, which I'll mention in just a second. So another example of a Haken manifold is a fibered manifold. So manifold fibers, three-manifold fibers of the circle if there's a submersion of the manifold to a circle. So each preimage of a point is going to be a codimension 1 submanifold, which is called a fiber. So in 3 dimensions, it's going to be a surface. So you obtain such a manifold by, if it's 3-dimensional and fibers over S1, then the fiber is a genus G surface, and you take the surface and you cross it with an interval, And then you identify one side with the other. So you take your surface, cross with an interval, and then choose some homeomorphism of the surface, which glues one end to the other. The submersion to the circle, I could just map this to an interval and glue the endpoints of the interval together to get the submersion to the circle. Does that make sense? And this manifold clearly has positive first Bay number. From the Seifert-Van Kampen theorem, the surface will be pi1 injective in the three manifold, so it's a Haken manifold. So this is a very explicit example of a Haken manifold. Was there a question, John? Right. So submersion means that there's no critical points of the map. Yeah, you can forget about submersion. Sorry. Just think about this picture here. Is that okay with you, John? Okay, sorry. Okay, so submersion. So if you have a map from a higher dimensional manifold to a lower dimensional manifold, then so if it's like 3 dimensions to 1 dimensions, then you can look at the differential at every point. And the kernel of that, if it's generic, will be 2-dimensional. So you're mapping 3 down to 1. So submersion means it's 3-dimensional, it's 2-dimensional at every point in the manifold. Is that okay? So there's no critical points. Like a Morse function on a manifold will have lots of critical points. So you can think of it, it's kind of like a Morse function without critical points, but to a circle instead of the real line. Okay, so anyways, it's not so hard to show that this is equivalent to this sort of picture here. And the theory of homeomorphisms of a surface is a very rich theory. So a motivating question then in 20th century three-manifold topology is given an immersed essential surface in a three-manifold, does there exist an embedded essential surface of the same type? So in some sense, this question encapsulates a good chunk of three-manifold topology in the 20th century. Well, why is this an important question? Well, it's because embedded surfaces are easier to deal with than immersed surfaces, than singular surfaces. So if you have an embedded surface, then, for example, if it's essential, then you can use the theory of normal surfaces, and it allows you to answer certain questions algorithmically about embedded essential surfaces in three manifolds. For example, there's an algorithm due to Jacob and Ortel that will tell you if a triangulation of a three manifold, if you're given that as your input, whether that three manifold is a Haken manifold. And there's an algorithm due to Haken originally that where normal surfaces sort of originated, or actually originated with Kneser, but Haken's algorithmic theory originated with an algorithm to tell if a closed loop of string is unknotted, whether it bounds a disk. So you can represent that disk in certain coordinates, and it's much easier than asking whether there's some immersed disk for algorithmic reasons. So that's one reason to be interested in embedded surfaces versus immersed ones. So anyways, whether or not this will be sort of the focus, and these are sort of the motivation behind some of Thurston's questions. So what are some examples of this question? Well, Dehn's lemma, which was proved by Dehn in 1911, except there was a problem with his argument, and it was resolved by this guy, Papakyriakopoulos, who was a professor here. So what this says, if an embedded loop in the boundary of a manifold is homotopically trivial in the manifold, so it lies in the kernel of the map of pi1 from the boundary to the manifold, then it bounds an embedded disk. So that's Dehn's lemma. And that allowed him to conclude, for example, if you have a knot whose complement has fundamental group equal to Z, then that actually had to be the unknot. So you can prove that from Dehn's lemma. That was his interest in this question. So there you're promoting this immersed disk that the loop bounds to an embedded one. Then the loop theorem was also proved by Kyriakopoulos in the same paper. It's a similar statement, except the loop in the boundary might not be embedded. It's just an immersed loop. And then the conclusion is there's some embedded loop in the boundary that's essential, and which bounds a disk in the manifold. And actually, you can conclude Dehn's lemma from the loop theorem. The sphere theorem is a similar flavor, so proved in the same paper. There's a very nice proof by Stallings later on, 1969, that takes advantage of some geometric group theory as well, and deduces the sphere theorem from the loop theorem. So if the second homotopy group of M is not zero, so it's not aspherical in particular, then so there's some immersed essential sphere in the manifold, in other words, because if pi 2m is non-zero, all you know is a map of a sphere that's not homotopically non-trivial. Then there exists an embedded essential sphere in M. Now, I'm saying immersed here. It's not completely obvious that a singular map of a sphere can be made immersed, but, yeah, question, yeah. Oh, okay, so, thanks. So by embedded, I just mean injects. So when I write a map like that, I mean that that the map is well, this just means it's one-to-one. You have to be a little careful in three-manifold topology. There's examples like the Alexander horn sphere or various wild sorts of things. Here, when I say embedded, so you can work with whatever category you want. So either, so it embeds either smoothly, so not only is it one-to-one, but the differential of the map, the tangent map, is injective at every point. And that's what I'll mean by embedded here. Or you can also work in the PL category, then if you have a triangulation of M, then sigma embeds if it maps triangles to triangles and it's also one-to-one. That's essentially, and that avoids some of these pathologies like the Alexander horn sphere that can occur in 3 dimensions. Oh, just immersed means that the differential, immersed means the differential is, so it's this, like a submersion where the differential has maximal rank everywhere. At every point. But now it may no longer be a one-to-one map. So this is an immersion of a circle in the plane, and this is, sorry, that's an embedding, and this is an immersion. There's a double point here, but it's still smooth at every point. Now, this difference for this talk is not so important. I said immersed here, but I could have just said a map. There's a general theory of promoting maps to immersions in 3 dimensions that, so I could have just said map, but I said immersion because it's essentially equivalent. Is there any other questions about terminology that I haven't really defined? Yeah. Yeah, I was being sort of vague. This is sort of trying to explain. So here, Dehn's lemma, you can say there's an immersed disk, then there's an embedded disk, or loop theorem, there's an immersed disk. So that's what I mean by the same type. But I was just being kind of vague. I mean, I don't want an embedded disk of embedded surface of much higher genus or something like that. So, the sphere theorem says there's an immersed sphere or map of a sphere that's homotopically non-trivial, then there's an embedded sphere. There's annulus and torus theorems in a Haken manifold. If there's an immersed essential annulus or torus, then there's an embedded one. So that's of a similar flavor. And then the Seifert-Fiberd space theorem says if the center of the manifold's fundamental group is non-zero and the manifold is aspherical, then M is Seifert-Fiberd. So it may not be clear here where's the surface, but there's a torus, it turns out. So if you have an aspherical three-manifold, then its fundamental group has no torsion in it. So any loop in the manifold will represent an element of infinite order. And if you think about the center, what does it mean for an element to be in the center? Well, so let's say this loop represents an element in the center of pi 1 of m. Again, I'm sort of ignoring base points. Then if I take any other loop in the manifold, the two commute. So there's going to be, I can sort of pull this loop around, and I get a torus in the manifold that's sitting inside of there. But it might be highly singular. The conclusion is that if you have this circle that commutes with every element of the fundamental group, then that implies the manifold Seifert-Fiberd. And I guess I also forgot to define Seifert-Fiberd. So Seifert-Fiberd means there's a foliation by circles. There's a Seifert-Fiberd three-manifold. That's false in higher dimensions. So actually, Seifert-Fibration is a little more technical to define, but this is proved by Epstein to be equivalent to there being a foliation by circles. So if you have this loop that sort of commutes with every other element in the manifold, then you can actually make that sort of geometric where you see this loop, you actually see this foliation by these loops. And when you go from one loop to another, then they're sweeping out the manifold. So foliation is locally, so through any point there's a unique circle. You can think of a foliation as a vector field on the manifold in which if I follow along every flow line is closed. So that's a one-dimensional foliation of a manifold. Okay, so this Seifert-Fiberd space theorem was a work of many people ending in the 90s, Peter Scott, Jeff Mess, Tukya, Kasten-Young-Rice, and Gabai. So all these theorems have in common that you're promoting some map of a surface, an essential surface in the manifold that is singular to one that's embedded. Well, as was known to Waldhausen, there's an infinite class of aspherical Seifert-Fiberd spaces which are not Haken. So a general example, maybe I should give another example of a Seifert-Fiberd space. If you take a surface and you take the unit tangent bundle, so you look at, in every tangent space, you look at all the vectors, so you can put some, say, Riemannian metric on it or something, but just think of taking a circle inside of the tangent space at every point. Then that manifold that's a three-dimensional manifold, and it has a foliation by circles. Because through any vector, there's a unique circle of tangent vectors through that tangent point. And it turns out that you can create these Seifert-Fiberd spaces. So here, there's an embedded torus. I can take any closed loop, and I take the unit tangent vectors at every point, and that forms pi 1 injective embedded torus into the manifold. If I were to take an immersed loop here, then that forms the unit tangent bundle over that is going to form a singular torus that has these double points lying over there. It has a whole double curve. So that's sort of the idea here, is that you have this potentially immersed torus in the manifold, or singular torus, and then you promote it to some embedded torus. Except there's these exceptions that had to be dealt with, and those were dealt with by Kasten-Young-Rice and independently by Gabai in the 90s. was it 94 or so? I forget. 93, okay. Now, these classic theorems of three-manifold topology are now really subsumed or superseded by the geometrization theorem. This was, again, question 1 from Thurston's list in his paper. And the geometrization theorem states that an irreducible three-manifold, so I could have stated this for aspherical manifolds, which I already defined. An irreducible manifold has the property that there's no embedded essential two spheres. So your manifold doesn't look like, and this is actually, I'm being a little bit careless here, but this is assuming like the Poincare conjecture and all that, but you have a two sphere in the manifold that separates the manifold into two non-trivial pieces. So this is denoted as the connect sum, M1 connect sum, M2. So it's not a non-trivial connect sum, in other words. Then it's an irreducible manifold. So if you have an irreducible manifold, then it emits, well, here is possibly non-orientable, incompressible surface. So it's a pi1 injective union of tori and Klein bottles, which is unique up to isotopy. So I can wiggle these tori around the manifold, but they're unique up to isotopy. And each component of the complement of these surfaces emits a complete locally homogeneous Riemannian metric of finite volume. And there's 8 possible model geometries for these metrics. So these metrics were introduced by Bill Thurston in the 70s. And so it's formulated here at Princeton, and he gave lectures on these, which are now sort of classic notes that have been reproduced by Princeton over the years and distributed. I got like a bootleg copy when I was a grad student. And he proved it for Haken three manifolds. So, and he conjectured that it holds in general. So this is, again, another reason that people were interested in this virtual Haken conjecture as a possible approach to proving the geometrization conjecture. Although it turned out that, well, Perelman gave a proof of the geometrization conjecture around 2003, although it took many years for people to sort of sort it out and write down a careful argument. But it's generally accepted now that Perelman's proof is generally correct. So using Ricci flow, it was a program of Hamilton who introduced the Ricci flow in the 1980s. And again, today I don't have any time to go into the general formulation of the geometrization conjecture. But suffice it to say that it was proved without using a lot of these this classical theory of three-manifold topology. It was pretty much completely independent. It was replacing a lot of those techniques with other techniques. So like the proof of the sphere theorem, for example, is proved, sort of comes out of their proof using some minimal surface theory. But it was really largely independent. And for this work, Perelman did not receive the Fields Medal or the Clay-Moronian Prize. I tried to give it to him. Did not accept it. Yeah, okay. He did not receive them. Now, again, I'm not going to get into all these homogeneous geometries. There's one of these geometries I've sort of drawn here for a unit tangent bundle of the surface. There's a nice homogeneous metric that you can put on there. But for the purposes of these talks, I'm going to be most interested in the hyperbolic case. So, and this is sort of the most interesting and least understood homogeneous geometry of these 8 Thurston geometries. So that's the one I'm going to focus on for these talks. And if you want to learn about the other geometries, you should go read Thurston's paper, which again, I highly recommend. So what's hyperbolic space? Well, one possible model for it, you make a chunk of glass that has the unusual property that its index of refraction varies, and the speed of light is proportional to the height above the table. So, So light can never reach the table because its velocity will go down to 0. And if light's taken the shortest path, it'll either go in vertical arcs or it'll go in semicircles perpendicular to the table. So this is one possible model for hyperbolic geometry, and could potentially be realized physically. Well, manifolds that are modeled on this geometry are called hyperbolic three manifolds then. And really what I mean is that there's a complete Riemannian metric of constant curvature -1. And the fundamental group of this manifold is what's called a Kleinian group. So as Dave mentioned, the isometries, the orientation-preserving isometries of hyperbolic space so the orientation-preserving ones are isomorphic to PSL2C. This is one of these special coincidences of isomorphisms between small-dimensional Lie groups. It's also isomorphic to PO31 in a different, this can be seen from a different model of hyperbolic space. Or maybe I'll go back to this hyperbolic space picture here. So I have H3 here is the notation for hyperbolic space. The boundary of H3 is corresponding to the table. This is actually can be identified with a complex plane. And then these 2 by 2 matrices are acting by linear fractional transformations on the boundary, which probably everyone's seen in complex analysis at some point. There's actually a point off in infinity, so that it closes up to form a sphere. So it's a sphere at infinity of hyperbolic space. And these transformations act in a way that, well, they can either, the generic transformation will fix 2 points in the boundary and will preserve one of these hyperbolic axes acting as a translation along that axis. Classic examples of hyperbolic three manifolds are the Seifert-Weber dodecahedral space, the figure 8 knot complement, and the Whitehead link complement. So here's a picture of the Seifert-Weber space. So you take a dodecahedron and you glue opposite sides in the way that's prescribed here. So you glue it with a twist, and you glue all pairs of opposite faces in the same way. So all 6 pairs with this twist. It turns out you get a closed three manifold when you do this. You can do this with an arbitrary polyhedron and see what you get. If you do the lesser of the twists, so if you here we're rotating by two notches or 2.5 notches. If you rotate the least amount, then you actually get the Poincaré dodecahedral space, which is the famous example of Poincaré that showed that his Poincaré conjecture, his original version, was false. But if you glue it with this larger amount of twist, then, I think I was, so it'll turn out that you get exactly 5 dodecahedra meeting every edge. And what you can do is you can make a hyperbolic polyhedron with dihedral angles of 2 pi over 5, and which is completely symmetric otherwise. And you glue these faces together by isometries, and they'll line up flushly around every edge. And by what's called the Poincaré polyhedron theorem, you get a manifold that emits a hyperbolic metric. So every point is going to be locally isometric to hyperbolic space. It'll be around the edges because of the 2 pi over 5 angle, and around the vertices, well, by Poincaré's sort of inductive argument. So this is a classic example. This is one of the first examples, or one of the easiest closed examples to understand. Well, in the 70s, Robert Riley discovered that there is a hyperbolic metric on the figure 8 knot complement. He actually found a presentation from the fundamental group and found a faithful representation in PSL2C, and then used a theorem of Waldhausen to conclude that it was actually homeomorphic to the figure 8 knot complement, the manifold that he obtained. But Thurston gives a very explicit example in his Princeton lecture notes. And if you can understand that construction, then you're bound to be a three-manifold topologist. So this is one of the simplest hyperbolic manifolds, which is non-compact. So when I say drill out the figure 8 knot, I mean drill out a compact neighborhood of it. So what you're left with is non-compact. And there's a hyperbolic metric on the complement that's finite volume, and where this torus here, that's the boundary of a tubular neighborhood, is off at infinity. So this is the it's the complementary space, and I'm thinking this figure 8 knot is sitting inside of free space, the 3 sphere. So you put a point off at infinity to make the hyperbolic metric. So it's only non-compact here near the knot. And here's another example, the Whitehead link. Actually, the hyperbolic metric on this example is a little easier to understand. This is made from 2 ideal octahedra, and this is made from 2 ideal tetrahedra. Oh, sorry, this is 1 octahedron, this is 2 tetrahedron.
You say Klein, you mean finite volume?
Yeah.
When you mean finite volume, when don't you?
Yeah, these are examples of finite volume Kleinian groups. I think maybe the original use of Kleinian group might have been a little different, but it's been subsumed. Like any good brand, it sort of gets expanded over time. What?
You mean finite volume?
No, I don't here actually. So if you have a complete hyperbolic manifold with a complete Riemannian metric, constant curvature, then the fundamental group's the Kleinian group. So there it doesn't have to be, in that definition, it doesn't have to be finite volume. And yeah, so I'll get to examples in a sec that are not. And actually, Kleinian groups are slightly larger than that. They can be orbifolds too, but I'm not going to talk about that in these lectures. Another remarkable thing that Thurston showed in his notes is that if you take the figure 8 knot, there's an operation of Dehn surgery. Actually, the notion of surgery comes out of 4-manifold theory and thinking about Morse functions on 4 manifolds and how the 3-manifold changes when you go through a critical point. But for the purposes of 3-manifold topology, how can you create new 3-manifolds out of old ones? Well, you take a knot and you remove a tubular neighborhood of it, and you glue a solid torus in. Well, if I have a solid torus, then there's a unique curve on the boundary that bounds a disk inside the interior. So I'm just thinking of like a donut or a bagel. And this loop here bounds an embedded disk. So I can attach this torus by any homeomorphism of the torus, and actually the diffeomorphism group of the torus, or the mapping class group, acts transitively on simple closed curves. So I can take this curve to any curve I want. So if I take it to a curve on this torus here that wraps p times around the meridian and q times around the longitude, then this is called a P over Q Dehn filling on that knot. And it creates for you a closed 3-manifold. Remember, this knot is sitting inside of the 3 space, so it's, when you glue this torus back in, it's compact again. So if I glue it along the meridian of the knot, I just get back the 3-sphere, but if I glue it along some P over Q curve, then I get a 3-manifold. Now, the remarkable theorem of Thurston is that all but finally many of these Dehn fillings on a hyperbolic 3-manifold are hyperbolic, so that it's not too hard to prove that this gluing is uniquely determined by the slope of this curve. So when I say finally many, I mean there's finally many rational numbers, so that if you exclude those, the rest of the Dehn fillings will give you hyperbolic manifolds. And he proved this by taking this complete hyperbolic metric on the figure 8 knot complement here and doing a deformation of it. So you deform the representation of PSL2C, and he proved that that can be completed to get a metric that actually exists on this Dehn filled manifold if you choose the representation very carefully. So this gave lots and lots of examples of hyperbolic manifolds that sort of weren't known to exist classically. It also gave a lot of evidence for his geometrization conjecture. So this is giving infinitely many, for a given knot, if I do Dehn fillings on it, all but finally many of those will be hyperbolic and therefore satisfy the geometrization conjecture if you start with something hyperbolic. And Thurston proved that if you have a knot that's knot of a very simple type, it's not a torus knot or not a satellite knot, then it actually has a hyperbolic metric. That's one consequence of his geometrization theorem for hyperbolic manifolds. And so that gave lots and lots of evidence for his geometrization conjecture. Now, Thurston also proved that these hyperbolic Dehn fillings on the figure 8 knot complement are not Haken manifolds. They don't contain any embedded pi1 injective surface. So now I'll define what virtual Haken means. So we call a compact aspherical 3 manifold as Haken if it contains an embedded pi1 injective surface, like I was saying. The Seifert-Weber space was also shown to be non-Haken recently by Burton, Rubinstein, and Tillman. And there they had to use extensive, rigorous computation using normal surface theory. And they're using some pretty sophisticated computational techniques. So a 3 manifold is virtually Haken if there's a finite sheeted cover, M tilde covering M, such that M tilde is Haken. And this term virtually means up to finite index or up to finite sheeted covering. So if you're talking about virtually a manifold virtually having a property, it means there's some finite sheeted cover that has that property. And if you can also talk about virtual properties of groups, and then you're talking about a finite index subgroup. So a finite sheeted cover of a manifold, here I'm assuming everything's connected so that it's a connected cover. This will be in one-to-one correspondence with some subgroup of the fundamental group, or some conjugacy class of subgroup of the fundamental group that's finite index in the fundamental group. Now, even though these Dehn fillings, hyperbolic Dehn fillings with the figure 8 knot complement are not Haken manifolds, they are virtually Haken. That was proved by Dunfield and Thurston in 2001. Now, Waldhausen conjectured that every hyperbolic 3 manifold is virtually Haken, so that's been known as the virtual Haken conjecture. It originated as a question in Waldhausen's paper, but it's been promoted to a conjecture, and it actually wasn't even conjectured in Thurston's paper. More strong question is, does it have a finite sheeted cover, M tilde of M, with positive first Bayen numbers? So that's question 17 in Thurston's list of questions. And again, as I explained before, if it has positive first Bayen number and it's an aspherical manifold, then it's a Haken manifold. So there's a non-separating surface in there that's incompressible. Oh, yeah. Yeah, that's a good question. So why did Haken define this notion of a Haken manifold? Yeah. Well, as I mentioned before, Haken had this algorithm for recognizing the unknot. And the point of that was that you have some disk that bounds a knot. So it's an unknot if and only if it bounds a disk, because you can just sort of contract it down to a loop along that disk. So how do you find that disk algorithmically? Well, he has this normal surface method of finding this. And what Haken realized is that that normalization procedure applied not only to disks like that, but it applied to incompressible surfaces in general. And so having these incompressible surfaces allowed him to operate as sort of normalizing procedures. What happens if you do that with a general surface? If it's compressible, you can have these handles that pinch off, and the surface topology can change. And that's actually these pinching off procedures called a compression, which is where the notion of incompressible comes from. And it's nothing related to incompressible fluids or anything, but it's just the terminology. So that's why Haken was interested in these manifolds. He called them sufficiently large manifolds, I think, and that was the terminology for a while, but then people started calling them Haken manifolds, I think, in the 70s or 80s. And so that's the terminology used now. They have other nice properties. You can characterize them as the fundamental group has property Fa of Serre, and they act non-trivially on a tree. They're non-trivial amalgamated free product or HNN extension. There's various characterizations of them. And it allows you to perform certain inductive procedures. So Waldhausen was interested in Haken manifolds. He proved that the fundamental groups have a solvable word problem, and he proved that they're homotopically rigid, the Borel conjecture for these Haken manifolds. The Borel conjecture says if you have an aspherical closed manifold and it's homotopy equivalent to another aspherical closed manifold, then the two manifolds are homeomorphic to each other. So that was another part of the motivation for understanding these Haken manifolds, in that these conjectures were known. Now again, a lot of this is subsumed by the geometrization conjecture. So a lot of the motivation, I think, for understanding these Haken manifolds was understanding questions that surrounded or were implied by the geometrization conjecture. Nevertheless, I think it's still somewhat interesting. Oh, yeah, another question. Yeah, so properties that are preserved, yeah, so if you're a hyperbolic manifold, then any finite sheeted cover, it's still hyperbolic. If you're separate fibered, any finite sheeted cover is separate fibered. The homotopy rigidity piece, that now follows from geometrization, but it was a big piece of work of Peter Scott to prove that like homotopy rigidity holds if you're only virtually separate fibered, things like that. Sorry, I'm saying, I think I'm misattributing there, but anyways, there was a lot of work done on that. Is that? The interest in being virtually Haken? Yeah, I don't really have a good explanation for that, I guess. It's just, I mean, it was sort of maybe historically interesting as an approach for the geometrization. Again, these Haken manifolds have nice algorithmic properties. I think that maybe the virtual fibering question, so M is virtually fibered if there's a finite sheeted cover that fibers, is maybe a little more surprising. So you take, this surface across an interval, you glue one end to the other, and then you mod out by a finite group of symmetries. And every hyperbolic three manifold is obtained this way, which is what Thurston's conjecture is saying. So if it fibers, as I said before, it has positive Bethe numbers, so it's stronger than asking for positive Bethe number. There have been a lot of work done on this question of proving various classes of hyperbolic three manifolds virtually fibered, done by this list of people here. So there was a lot of interest in this question. And so this was Thurston's question, number 18 in his list. Are hyperbolic three manifolds virtually fibered? So there's known manifolds which are not virtually fibered, like this unitangent bundle to a surface of Euler characteristic less than 0 is not virtually fibered. Nevertheless, it's also constructed out of some kind of fibration. So, anyways, this is, I think, an interesting question, just sort of intrinsically. Can you obtain every three manifold or most three manifolds by taking a mapping torus of a surface and diffeomorphism and then modding out by some finite set of symmetries? So if we have a finite volume hyperbolic three manifold and a map of a surface in there, which is essential, so it's pi1 injective, then there's a certain dichotomy for the geometry of the surface. So discovered by Thurston and proved by Bonahon in general. It's either geometrically finite or geometrically infinite. So the first case includes quasi-Fuchsian surfaces, which I'm not really going to have time to explain carefully, but the second case is geometrically infinite. In this case, the surface is virtually the fiber of a fibering. So the tameness theorem of myself and Caligari and Gabay proves, plus the Canary's covering theorem implies a similar dichotomy for finally generated subgroups of a Kleinian group in general. Either the subgroup is geometrically finite or it corresponds to a virtual fiber. So this is another reason to be interested in this virtual fibering question from the perspective of Kleinian groups. So what's a quasi-Fuchsian group? Well, it's a Kleinian group. Here's the complex plane, or part of the sphere of infinity of hyperbolic space. And it's a fundamental group of surface which acts by these 2x2 matrices and which leaves invariant some circle. Topologically, this is a circle. It has higher Hausdorff dimension greater than 1. And this is what's called a quasi-Fuchsian group. So on the other hand, the geometrically infinite groups, they occur as fibers of fibrations. It turns out they limit to any point in the sphere of infinity. So you take any point in the sphere of infinity, you look at its orbit into the group, and it'll be dense in the sphere. So the limit set is everything. But there is associated with them certain sphere-filling curves, which are piano curves. And here is some kind of subdivision. You can get these things by like one interval. If I divide the circle into two intervals, one interval will carry this tile, and the other interval will cover the complementary tile. So it's like the construction of a Hilbert curve or a Sierpinski curve. And then I can subdivide that interval, and now one half will cover this part, and one half will cover this part. So it's doing some walk through here, and then some walk through here. And if I keep subdividing, then I get this sort of path. And so you see this sort of approximation to the curve where it's going to fill up, it's going to be the sphere-filling piano curve, just like a Hilbert curve or something. Okay, so let's see, I guess I'm running short on time. Do I have like, how much time do I have left? Like 3 minutes? It's
Maybe 5 minutes.
5 minutes? Okay. Let's see. So, so you can ask this question, given a map of a surface in M with Euler characteristic less than 0, is there an essential embedding of the surface into M? And the answer to this question in general is no. So, well, as I mentioned, when the Euler characteristic is 0 for tori, there's these small Seifert-Feired spaces which are where they have no embedded torus. But Thurston, as I mentioned before, proved the Dehn fillings on the figure 8 knot complement are non-Haken, whereas it was proved by Cooper and Long and Tao Li in 2001 that these manifolds all contain immersed pi-1 injective surfaces, or most of them do. And in fact, as I mentioned also, 2002, Dunfield Thurston showed these manifolds have finite sheeted cover that's Haken. So these are examples which have immersed surfaces, but they don't have embedded ones. So you can't just sort of cut and paste the surface and get something embedded. Now, under certain circumstances, you can answer this question as yes. So Gabai proved if you have a map of a surface in the manifold with Euler characteristic less than or equal to 0, and it's non-trivial in homology. So here's the fundamental class on homology of H2 of the surface, and I map it into H2 of the manifold, and it's non-zero. Then there's actually an embedded surface, sigma prime, which embeds into the manifold such that it represents the same homology class in H2, and has Euler characteristic no smaller than the Euler characteristic of the singular surface. Here I'm being a little sloppy with, you should assume there's no two spheres in sigma prime that's connected or something. Well, sorry, it might be disconnected, but no two sphere components. And Gabai's proof makes use of an inductive method called sutured manifold hierarchies to construct a foliation of the manifold with an embedded compact leaf, and gets the lower bound by an Euler characteristic argument analyzing the Euler class induced by the foliation. So it's quite a remarkable argument. And some of these ideas go back to Thurston. Now, there's a theorem proved in 2009 by Kahn and Markovich, Jeremy Kahn and Vlad Markovich. Kahn spoke here in May at the Browder conference, Panorama Topology. So hyperbolic three manifolds, closed hyperbolic three manifolds contain immersed quasi-Fuchsian surfaces which are arbitrarily close to being totally geodesic. Now, I said that a quasi-Fuchsian surface has limits at this circle. It's fixing this circle topologically on the boundary infinity. But this is saying you can get these surfaces whose circles can be made arbitrarily close to being a round circle. So this wild limit set that I drew, it'll still be rather wild. If you look at it very closely, it'll be fractal-like, Hathorth's dimension greater than 1. But you can make it as close as you want to a circle. So in some tubular neighborhood of a circle, I can fit one inside of there. There have been a lot of previous work on this problem. I mentioned these before. Cooper, Long, and Lee proved that, gave lots of evidence for this question. And actually, in a cos hyperbolic manifold like the figure 8 knot of the Whitehead link, the non-compact finite volume manifold, Masters and Zhang showed their essential quasi-Fuchsian surfaces. So there's no parabolics in there, which is not obvious at all. And just before this theorem was proved, a very general version was proved by Lackenby in 2008, that if you assume you have a hyperbolic manifold that's arithmetic, and again, for sake of time, I can't explain what arithmetic means, but suffice it to say that it's a fairly large but very restrictive class of hyperbolic three manifolds. Contains a closed essential immersed surface. So he proved this theorem just maybe a few months before, actually, Kahn-Markovich, or, well, anyways, very, very soon before. Okay, so now I wanted to talk about, the next topic was properties of three manifold groups, but since I'm almost out of time, I might have to, start with, maybe it makes sense to start with this tomorrow instead. The next lecture will focus on geometric group theory. Well, I'll talk about these group properties, and then the third lecture will be discussing this work of Donnie Wise. So we're going to translate these questions of Thurston into questions of geometric group theory via the Kahn-Markovich theorem. And these lectures are dedicated to the memory of Bill Thurston, who, as many of you know, passed away in August this year. So that's it for today.